All right. Everybody ready for an exam? Is your heart beating a little faster right now? Everybody awake? Could somebody tear out a sheet of paper and pass it around for everyone to sign in, please? Huh? I don't know. I'd have to look at the schedule. You in a hurry?
No, you just said you're ready.
I just wanted to get everybody's heart beating a little faster, see if I could wake y'all up. So we left off Monday. This is Wednesday? Yeah, we left off Monday. We had fired an arrow with an initial velocity of 50 meters per second at an angle of 20 degrees. And we wanted to find out how far away it would be when it hit the ground. So the first thing we did was to ask, how long will it be in the air? And in order to find that out, we looked at the equations of motion. We looked at the vertical components to determine the time of flight. How long will it be in the air before it hits the ground? We converted our initial velocity vector into the two-dimensional coordinate, rectangular coordinates. So we could treat the vertical component and the horizontal component of the initial velocity vector as separate quantities. We already have the acceleration, the constant acceleration, as in two separate quantities because there is no horizontal acceleration. All of the acceleration is the constant 9.8 meters per second squared of gravity. We filled out the equation of motion and got it into the quadratic form, solved for time, for t, and we found out that the arrow would be in the air either minus 0.085 seconds or plus 3.58 seconds. So the first question I've got for all of you: what is the interpretation of these, of these two different times? How could it fly in the air for minus 85 milliseconds? What does that mean? Think back, because we talked about it. Yeah, kind of. Look at, this is what we're measuring. We're dealing with the vertical motion of this arrow. And we're starting it off at t equals 0 and y equals 1.5 meters. Here is y equals 0 meters. And we send it off at an angle, and we ask, this is t equals 0. We're asking, what is t here when this trajectory hits 0? And we found that this is 3.58 seconds. But that's not the only time this trajectory would hit 0. It would also hit 0 at t equals minus 0.085 seconds. That's the meaning of this this is in fact, this is one of the lessons that from the book, that they only mention it briefly in passing, but it's important, and that it's at this right here. What does that equation tell you about ballistic motion or projectile motion? Mathematically, this is telling you that the motion, the flight of a projectile under constant acceleration due to gravity and no horizontal acceleration, that motion is going to be parabolic. This is the equation, the mathematical equation of a parabola. So you're always going to have, if you have no horizontal acceleration and only constant acceleration due to gravity, then your motion is always going to be a parabola. Okay? Which means you will solve for a quadratic equation. That means for any value of y that you're looking to determine when it reaches, there's going to be two answers. One here and one here. We can choose y at t equals 0 arbitrarily. Okay, we can pick any point in that timeline and call it t equals 0. We could have set t equals 0 way back here. Now, of course, it would have made the equation extremely convoluted and hard to understand, but we could, and then we would have gotten two different numbers, but they would still have pointed to this spot on the timeline and this spot on the timeline. The book makes mention of this, and they point out that back in Galileo's day, this fact that all ballistic or projectile motion on Earth is going to be parabolic. That was big news back then. That was the focus of cutting-edge physics research and development. Today it's something that's pointed out in an introductory physics course. And it's just pointed out in passing. But it is still true. And you need to understand it, because basically that's what physics is it's learning how to use mathematics to describe the world that we observe and how to interpret it. So that's why pay attention, take notes, because I really do want y'all to understand this. This is something I really want you to wrap your minds around, is how to interpret what all of these equations and numbers mean. In this case, it means there are, in fact, two times when this trajectory will intersect y equals 0. It just happens that one of them would have happened before we shot the arrow, because we started off way up here. That shows up as a negative result. There are a couple of other unusual examples, unusual results that would give you a different result to this quadratic equation. And we have talked about them. So let's see who remembers. What is one of the other odd results you would get? What if we were looking for the maximum trajectory? The maximum height that trajectory would reach, that arrow would reach. If we wanted to know how high did it go when we fired it. Say again? We would be looking for the moment when velocity, the vertical velocity, up and down, v sub y, when it's equal to 0. And that would give us a y max. But what would we get if we solved the quadratic equation for when that occurs? What if we were looking for t when y equals y max? What would the result of that quadratic equation be? Remember, we're looking for a moment, and then we're looking for some time, and then that time plus some amount, and that time minus some amount. See? We're getting this amount plus or minus the difference. So when this time plus b squared minus 4ac gives you this time, or this amount minus b squared minus 4ac gives you this amount. The higher you go up that trajectory, the closer those two times get to each other. That means the smaller this difference is becoming. So that b squared minus 4ac is getting smaller and smaller and smaller until you get right here to the very tip top, and you only get one value of y, one value of t, where there's only one moment in time where it reaches the very tip top, and that's when it's t plus or minus 0. So when b squared equals 4ac, then you get this plus or minus the square root of 0, which is 0. And you get one and only one time. One and only one result. And that is this time, this moment, when the arrow reaches the very top of its trajectory, and it will not go any higher. And it starts coming down. What would happen if you said, I don't know, let's say y max, just hypothetically, let's say it's 50 meters. And that's probably not true, but it doesn't matter. I'm just picking a number. What if you tried to find out at what time will this trajectory get to 55 meters? What would happen? (4ac) would become greater than b squared. And you would suddenly find yourself looking for the square root of a negative number. See, this number here, this difference, down here it starts out big, and it gets smaller and smaller and smaller and smaller until it goes to 0 right here. And if you keep going higher, it goes negative. It goes from positive to 0 to negative. And when you find yourself looking for the square root of a negative number, what does that tell you? Say that out loud. It's not undefined. No, it actually would be an imaginary number. But what it's telling you and us in the context of this analysis is that we're looking for a time that will never happen. We're looking for a value that at a height that it will never reach. There will be no time when the projectile gets that high. Are y'all starting to wrap your mind around how this quadratic formula applies to the parabolic motion of a projectile? What other formula? The other kinematic equations? All right, let's write them down again so we can keep up with what we're talking about. If I can find them. There they are. Okay. We got V equals V naught plus AT. X equals X naught plus V naught T plus 1/2 AT squared. And we got V squared equals V naught squared plus 2A X minus X naught. And finally we have V average is equal to V minus V naught over 2. Now, the question is, can we use one of these other kinematic equations to solve for T? Well, the only other kinematic equation is this one, V is equal to V naught over AT. But, yeah, we use is this the one you're saying we start with to find the distance? V final. You're looking for V0, when the velocity is 0? So you're saying we can solve V final?
No. The V final from the third kinematic equation.
From this one?
Yeah, and then we can use the first one to get the time.
Okay. But in order to use this one, we would have to know the distance.
We know the distance.
Where do we have the distance?
We got in
We know that it starts at 1.5 meters, okay? And we know that it ends at 0 meters, why? But that does not tell us the total distance. That just tells us the displacement. We don't know. And now if V naught was in order to let's just take your approach. What do we know? We want to find V final, so we're going to look for V squared is equal to V naught, the initial velocity, which is well, the initial velocity is 50 meters per second, but that's not all in the vertical. It's only 46.9 meters per second in horizontal and 17.1 meters per second in the vertical. Okay, so we put 17.1 meters per second squared plus 2 times A times x minus x naught. Now, A is just gravity, so that would make this 17.1 squared minus 2 times 9.8 times x minus x naught. Or, well, actually, we're talking y minus y naught. So what would y minus y naught be? 1.5 meters. Okay. What's 2 times 9.8? Let's do the arithmetic. I don't have my calculator with me. Two times 9.8 times 1.5 is 263. That's with 17.1 squared. What is 17.1 squared? $292.4. Now what's 2 times 9.8 times 1.5? Minus 29.4. Okay, and that gives us, what was the total again? $263. Close enough. V squared is 263, so what is V? .4 meters per second. But didn't we already say that the initial velocity was 17.1 meters per second? And so now the vertical velocity is 5.4 meters per second. 16.2? Okay. .2 meters per second. Okay, what have we calculated then? But what is this telling us? When is it moving at 16.2 meters per second? Because remember, and this is actually a useful exercise here, because it's not just enough to be able to plug numbers into an equation and work the calculator if you don't know what the numbers mean. So we're calculating a new velocity. We start off with velocity, and we find out a new velocity 1.5 meters later. What is that telling us? Telling us that we're starting off here at y equals 1.5. With a velocity of 16.2 meters per second in that direction. I'm sorry, not 16.2, 17.1. And then somehow we're ending up here at 0 with a velocity of 16.2 meters per second. But if we're moving up with a positive velocity here, how did we end up down? With this negative acceleration. But this actually might not be, this might be a legitimate interpretation. Because we took a square root to get this 16.2, which means this is actually plus or minus 16.2. So this could very easily be, we could interpret this as minus 16.2 meters per second going down. Let's put a pin in this. Do we end up with V final, a Vy final equals minus 16.2 meters per second? Do we end up with that? Let's come back and check that when we finish analyzing the problem, okay? Because right now, what we know is that we loose this arrow and it is going to follow this trajectory and come land and hit y equals 0 3.58 seconds later. We can look at what will the velocity be at that point. But first, what I want to know is how far does it go downrange in that amount of time? Okay? So, we now look at our horizontal component of our motion. And our horizontal component of motion gives us a 46.9 meters per second is our initial velocity. So let's stick with what we know works. We've got x. We want to know x equals x sub naught plus v sub x sub naught times t plus 1/2 ax, our horizontal acceleration, times t squared. Okay? Well, we've defined this as starting point as x equals 0, so that's 0. And we have no horizontal acceleration, so that is 0. And that means we now have just x equals v sub naught in x times t, which is equal to 46.9 meters per second times t, which is 3.58 seconds. And that equals, someone with a calculator? 167.9 meters. Seconds canceled. And now we can draw this accurately. We start at y equals 1.5 meters and x equals 0 meters. we leave at 20 degrees, follow a parabolic trajectory, and land at a point x equals 167.9 meters, 3.58 seconds later. Now, let's look. What would the final velocity be at this point? How would we calculate that? Actually, probably would. In this case, we know that the let's back up and continue his thinking. Originally, your thinking was we would find this final velocity and then use it to calculate t from this equation, right? Okay. Well, we now know what t is. It's 3.58 seconds. Let's see what that gives us. If we set 16.2 meters per second is equal to the initial velocity of, what was our initial velocity? 17.1 meters per second? Minus 9.8 meters per second squared times 3.58 seconds. Okay? Someone do the arithmetic. What's 9.8 times 3.58? Say again? 35.08. This is actually looking pretty good, isn't it? Now what's 17.1 minus 35.08? Negative 17.98. That doesn't work. Oh, but wait a minute. We were looking to solve for t, right? Not final velocity. So let's do that. If we're looking to solve for t, we would say v final minus v sub naught divided by a equals t. So that would be 16.2 minus 17.1. What is that? It's what? Negative 0.9 divided by negative 9.8 gives us a time of 0.09 seconds. Recognize that number? What you just found out by going that route was the time that this trajectory would have started, not the time that it would have ended. Because you weren't taking into account the vertical motion upward before it begins its final descent. You were looking and just assuming that it's going to go straight down. And that would put you coming back to this point right here. Does everyone see what happened? What he just solved for? So do you see what you actually calculated? Yeah, you calculated not this time, but this one. See? Remember what I warned you about with the calculators, and when you start looking at angles and plugging in ratios and taking the inverse tangent? The calculator will give you an answer, but it won't necessarily be the one you're looking for. It's up to you to understand what you're calculating, to understand what the numbers that your calculator give you mean. Now, and I would also direct your attention to table 3.3-1 in section 3.6. It's on page 60. Here it gives you the general kinematic equations for use in 2 dimensions. If you'll recall, these were only for use in 1 dimension, when all motion was restricted to one line, to a horizontal or a vertical line. So since we're working in 2 dimensions now, let's take a look at these 2-dimensional equations and see how they relate and how we can simplify them. So we're going to start V sub x is equal to, you know what, let me go ahead and do this, because they're presenting them to you already broken apart into horizontal and vertical components. So we're going to talk V sub x is equal to V sub x sub naught plus A sub x T. And then we've got x is equal to what we already know, x sub naught plus V sub x sub naught T plus 1/2 A sub x T squared. And we've also got this one, V squared in x is equal to Vx sub naught squared plus 2A sub x times x minus x sub naught Notice there that we're looking for x, for the acceleration in the horizontal component. Similarly, in the y component, we would put v sub y is equal to vy sub naught plus ay times t, which is actually equal to vy sub naught minus 9.8 or minus g. put minus g times t. We can put y is equal to y sub naught plus v sub naught yt minus 1/2 g t squared. And vy squared is equal to vy sub naught squared minus g times y minus y sub naught. Now, and this is the one you were talking about using. Actually, I already did kind of simplify it because in all of these, you would be actually, I wrote in minus g for a sub y, for the y component of the vertical component of acceleration. But they give you a second table here, 3-2. Everybody looking on page 60? They've simplified these equations by making note that a sub x is always going to be 0. So v sub x becomes, well, v sub x naught. Your horizontal velocity is just going to be your horizontal velocity. It's not going to change. And it tells us that x is going to be x sub naught plus v sub x sub naught times t. And that's it. And that means this one becomes kind of superfluous. It just becomes the first one squared. So there's, I don't even bother with that one. This one v sub y is vy sub naught minus gt. And y equals y sub naught plus vy sub naught times t minus 1/2 gt squared. Just kind of what I already wrote up top, and the same with the last one. Vy squared equals vy sub naught squared minus 2g. Yeah, I left out the 2. Y minus y sub naught. These are now the general kinematic equations that we're going to be using when we're working in 2 dimensions. And generally speaking, because you're dealing with parabolic motion, because you're dealing with what is ultimately going to be a quadratic formula, it is very dangerous to try and take shortcuts like you were talking about doing. It is a simpler calculation to just solve for the final velocity and then find out the time in which that would happen. But you don't do at that point you have to really put some thought into the physics, because you can very easily find yourself calculating the wrong answer. Do we have any questions? Does anyone have any questions about any of the homework? No? Does anyone else have any homework that they want to turn in? Say again? Oh. All right. Well, what time is it? Yeah, we got another 7 minutes. All right, well, if no one else has any questions or any comments or thoughts, then I will see you on Friday. Say again? Yeah, normally, yeah. Y'all might want to have some questions about the homework ready on Friday. Say again?
You're going to do for? When are you planning on having it?
Did I miss giving y'all an exam?
No, I don't think so. I was just asking.
Yeah,
I know we've already taken it too.
Yeah, you just took an exam 2, didn't you?
No, I'm honestly not sure. All my classes. Especially with work.
Yeah.
All one long day.
Yeah, I would have to look at the syllabus. I tend to focus on what do I want to cover today, and then I'll worry about what's going to happen on Friday, or not necessarily Wednesday to Friday, but I look at what am I going to cover this week, and an exam wasn't part of it, so.
Okay, that's fine. Makes it easy.
You too. "11 minutes. Wish I had time to go get another cup of coffee, but I don't have time to brew it and get it. Oh yeah, thank you.